Okay, so first of all, thank you very much for listening to me talk about quantum communications at ORNL. So today I'm going to talk about just quantum communications and networking, but our group also does work on quantum computing and quantum sensing. And so it's really difficult to include all of our collaborators on this slide. So I only really have listed the staff and postdocs who've contributed to the work that is presented in this slide. It's kind of an overview of all the things that we do in quantum communications and networking, and sort of the latest of what we're trying to do and what we're trying to achieve in the lab. And so I really have to say that it's been a real pleasure collaborating with Professor Weiner over the years, and we're going to touch on a number of joint experiments as we go through this. So first of all, I wanted to mention that most of what people think about when they think about quantum communications is quantum key distribution. But what we've been doing lately is trying to expand upon that sort of narrow view and doing some additional protocols. So I'm going to spend the first bulk of the talk probably talking about that. And then I'm going to talk about some quantum networking experiments that we've been working on, and eventually where we want to go in trying to realize these quantum repeaters. So to motivate this, we had one of these workshops, which was mentioned earlier in my introduction, and this was sort of the first big workshop. Why should DOE be doing this? And really the answer is that if you're going to be developing quantum resources, you get much bigger advantages if you can network these quantum resources. So we could imagine building entangled sensor networks to probe new sectors for dark matter, as an example, but also for distributed quantum computing. So it's very possible that we could have quantum computing resources where we hit scalability limits to refrigerators. And so to build them to be into larger processes, we're going to have to densely connect them with quantum networks. In addition, there are applications where we like to remotely program quantum computers so we could realize blind quantum computing. And that would allow you to do computing in a way that was private. So for example, if you had protected data, like say health data, and you wanted to run jobs on a quantum computer, you would need to encode that, or you may well have to encode that on a quantum network so you could protect your data in transmission. And then finally, there's this quantum key distribution application. If you have an advanced optical network that's quantum fundamentally, then why not get the benefit of having quantum key distribution in there? Some challenges, really one of the biggest challenges is trying to figure out how to make quantum networks fit into our current infrastructure. So we have a classical network that's out there, and we're probably not going to make a completely separate quantum network. We're going to need the quantum and the classical networks to coexist on the same fiber infrastructure due to the cost of the fiber infrastructure. And so this is a challenge in exactly how we're going to do this. And we also are challenged in trying to figure out how to scale these quantum systems. And some of scaling is related to how exactly you correct errors. And then other aspects of scaling are really how it's talking to the classical network. And then we have potentially a need for transduction. So currently DOE is mostly focused on looking at optical signals that go down optical fiber. So typically we're talking C and L bands around 50 nanometers. If that's not the native energy scale of your quantum resource, then you're going to have to do transduction to go to whatever that happens to be. So for example, it might be a 10 gigahertz microwave photon for, like, say, a superconducting quantum bit. Okay, so the ultimate vision, we want to build a national scale quantum network. And so this national scale quantum network, we expect to be a combination of networks at different scales. So initially we start with a quantum local area network, which we have now, and I'll mention a little bit later. And then you start to build up these metro area networks, which are connections of quantum local area networks. And then eventually, if we have a quantum repeater, then we can build these wide area networks, which potentially could scale nationally. Okay, so we're looking at this problem in terms of many different phases. Okay, so now on to quantum cybersecurity. So first of all, I'm going to mention quantum key distribution. So the promise of quantum key distribution is we can use single photon states, and we can encode random numbers on those states and distribute them and make random measurements on them. And then we can do post-processing on that to have shared secret keys distributed between the people on the other ends of the quantum channel. And then if we had that, then we could take our information and XOR the information with our distributed keys, and then we could encrypt that information and send it along a channel in such that way that that information cannot be encrypted no matter how powerful a computer one has. We would call that information theoretic secure. And so that's the promise of quantum key distribution. And it's a symmetric technology, which means it's point-to-point. And also, that's one of the things that people said is kind of bad about it. So one of the things we're doing is looking into how we can use these kind of quantum cybersecurity protocols in point-to-multipoint ways. Okay, so I'm going to skip this about QKD. One of the things that we've really been focused on is looking at how do we go to the next bigger network. And so with QKD, it's pretty well established that one can use trusted relays. So if we just take a photon and send it down a fiber, there's a rigorous bound that says that for some amount of loss, it limits the amount of communication that we can do, quantum communication that we can do. And so people proposed and demonstrated how to do this with quantum key distribution. And what you do is you break the channel up into smaller links, and you terminate and perform QKD between these smaller links. And then what you can do is you can take the classical key material and you can do an XOR with the neighbor, and then you know, by taking that material and hopping it down the road, you can distribute shared keys over longer distances. And so this is something which we've been working on recently in terms of the energy infrastructure. This is because the energy infrastructure is a really great use case for quantum key distribution. So we have naturally these nodes where we're able to take our key material and break it out and talk to another neighboring QKD system, because these substations, these electrical substations, they have physical security and they also have surveillance. So shown on the right here down at the bottom, we have physical security. Let me turn on my laser pointer here. We have physical security in the substation. They also have surveillance. This is a photo of a wall that is sitting in the operations center at EPB, which is a utility in Chattanooga, Tennessee. So we've been partnering with them and doing demonstrations down on their network. And so if there's ever movement in one of these substations, these cameras will actually bring the focus to the operator's attention, so that way they can investigate. So these substations offer us a really great place to do this trusted node type of work. And also the way that grids are laid out is they're very concerned with power loss. And so they're arranged very linearly, and that sort of matches very well with this trusted node architecture. Now, the other reason that it makes a really good use case is that when you deploy these grid infrastructures, you want them to last as long as they possibly can. So you might deploy something that you want to last for decades. And so as we're doing upgrades to the smart grid, the tendency is to actually utilize IT, like IoT type communications. And that's not really typically built for long-term security. And so what we're trying to do is have a sort of different approach to give us long-term security for these devices, so they can last decades and decades, and you're not going to have to worry about your communications cybersecurity. Okay, so then finally, typically we have, this is a 60 hertz system, so it's a relatively low amount of data low bandwidth data that you have to deal with. Okay, so we did a number of demonstrations. First one we did a couple of years ago with Los Alamos National Labs, where we did what's called a loopback scenario, where we take our quantum signals and we start over here in the operations center. We have a couple QKD systems here, and we send our quantum signals down, and then we come around backwards and come back. And so what we did is we tested the QKD systems that we had over these different loopback lengths. And so we wanted to make sure that we would work on the installed infrastructure. So this is what it kind of looks like logically over here. And then this is what the data looks like. And we can see that we have the quantum bit error rate, which is a measure of the quality, and we have the generated secret key rate. And you can see that it's really noisy here early on, and it kind of calms down, and it gets really noisy again for both of the systems. And for the two systems that we used different encoding approaches over this fiber infrastructure. And if you go back to that map that I showed, most of that map, the fiber is hanging between the utility poles. So it's free to move around when the wind blows. And sure enough, when we correlate the data that we took with the weather data, it was a pretty warm day when we did this in 2019. And you can see that when the wind is blowing really hard, it correlates with higher error rate in especially our polarization encoded data. So fast forward, now that we had all of that stuff working, we wanted to make this a little bit more complicated. And once you go from a scenario where everything's co-located in one lab and you're just doing loopbacks to the scenario where everything's spread out and distributed, that's actually a fairly big leap in complexity in order to get the whole system to work. And so we did this just last year. We had 3 QKD systems, one from Cupitech, one from Los Alamos, and one from ORNL that we put into this network. And we have a system where we basically decided to make a network level key that was 256 bits, since all the key rates were being generated differently. And we're able to do this successful relay across this network. And this paper has just been accepted in IEEE Access just recently, and it's on the archive if you want to take a look at it. Okay, so now continuous variable key distribution. So most of what I've been talking about so far has been a discrete variable quantum key distribution where we encode it in polarization, but there's another approach out there which encodes in the amplitude and phase. And so to motivate why we are working on continuous variable quantum key distribution, we're going to go back to the Wayback Machine here. And we're going to look at a vision that we had in this paper that we wrote jointly with Los Alamos back when I was at Telcordia Technologies. And our vision was we want to make quantum key distribution practical and work in real optical networks because there's a real value in networking multiple users together in terms of the network's usefulness. And so we had this idea that we could multiplex quantum key distribution and classical signals together on a shared fiber infrastructure. And so we did some initial work on that. And here's some pictures of the experiment that we did back then. And this is the first time anybody had actually gotten quantum keys generated while using this an infrastructure that had signals that were classical level. Co-propagating in the fiber. And so really in this paper, we explored the physics of the impairments that you get, four-wave mixing and Raman scattering. Raman scattering is the one that's really hard to deal with because it's broadband, and it's linearly increasing with the channel power, the classical channel power. And so what we did is we mapped out how this degrades our quantum key distribution system, and we couldn't even get up to a milliwatt of launch power before we were stopped in our ability to do quantum key distribution. And that's a bad thing because typical launch power of a classical channel is a milliwatt. And so this is a pretty strong limitation if you want to do just QKD, not to mention even quantum repeaters, which are a lot harder to do. And so what the community basically decided to do was, well, we'll just turn down the classical channel power so we don't have to deal with the Raman scattering. But there's a better thing that one can do, and that's proposed in this paper by Bing Chi when he was at University of Toronto. Basically, because the Raman scattering is broadband, if you instead go to a continuous variable encoding, then that gives you the capability to use homodyne detection, which is basically an interferometric way that you can detect your signal. And so it allows you to basically screen out almost all of the Raman noise. And so it just, it works so much better if you've got co-propagating classical signals in terms of being able to operate. So
this is the Raman scattering from the fiber material?
That's right. That's right. So it's naturally Raman scattering from the fiber material. And that's assuming that you've already done all of the work that it takes to make sure that you have sufficient isolation so that your lasers aren't leaking through your filters into your quantum channel. That Raman scattering, you basically cannot get rid of it. Okay, so we've built some CV-QKD systems in our group. And Bing Chi's been working on this for a number of years in the group, and he has this really nice paper that was in PhysRevX a number of years ago. And actually today, Bing's down at EPB trying to demo this type of local oscillator-based continuous variable key distribution in a real-world environment down at EPB. So that's never been done. It turns out it's really hard to do this, to make this go from a laboratory experiment, something that can actually go out in the real world, and then do this phase recovery method. So that demo is ongoing as we speak, and it's going to be pretty exciting if it works. One of the things that we're really concerned with CV-QKD is how does it fit into the real world? In addition to be able to send your optical signals along with that shared fiber infrastructure, what we want to do is we want to move the technology to a point where it naturally fits into the transmitters and receivers that coherent communications companies are dealing with. So in communications, the bandwidth is really valuable. And so to improve the spectral efficiency, the communications industry, instead of turning on and off your optical signals to encode information, they're moving to coherent systems now. And so they can use, but by encoding in amplitude and phase, really big symbols. And so what we want to do is we've been working on trying to answer the question, can we move to a system where maybe for some nominal extra cost, we could take a coherent communication system and then make it, quote, quantum grade. And then you could go and buy the hardware that would either work as a QKD link or as a coherent communications link. And so as a stepping stone to that, we talked to a lot of different coherent communications companies. And we found one that was willing to work with us and try to make a quantum grade receiver. And so what we did was we told them the important things that have to happen, the specs to meet to get a quantum grade receiver. And as a result, what we did is we started with a box like this that takes a PhD with years of experience to tune up appropriately. And now what happened is Optiplex actually sells this receiver, and you can just go buy it. It costs about $10,000. It's kind of a state-of-the-art detector for CV coherent comms. And in comparison with state-of-the-art detectors for discrete variable qubits, which are superconducting detectors, it's a big cost savings. And it's also a stepping stone towards trying to realize a quantum classical continuous variable system. So we're pretty excited about that. We're also working on some integrated optics kinds of things, which is kind of related more to this next slide. So one of the ways that we're looking at is to try to do integrated optics to do passive encoding. So if I had, let me just explain the idea of this slide first. So we did this in bulk optics. The idea here was we take a noise source, like an amplifier or a superluminescent LED, and what we do is that's going to be emitting light with random amplitude and phase fluctuations. So we take most of that light and go immediately and detect into a dual homodide detector, so we're measuring the amplitude and phase fluctuations and recording those as a function of time. Well, since those are random, we can attenuate the other portion of that light and transmit it to Bob, and then Bob can measure those amplitude and phase fluctuations basically as a quantum signal, because we attenuated it here and sent it over the channel. And so what this gives us is an ability then to have a passively encoded continuous variable transmitter. And the reason why that's important is that it removes the complication of trying to get high performance modulators on chip. And so here's a little plot of the quadratures as measured from the source, and then we can then look at this in terms of the correlation that Alice and Bob share as a function of the attenuation, and then we can translate that into expected quantum key distribution performance. So we're working on getting this implemented in chip right now. Okay, so the next thing I want to talk about is more of a computer communications project, but it's a stepping stone toward making this more practical on smart grid environments. So what we have here is a demo that we did earlier this year where our goal was to leverage commercial hardware. So we used Qubitek's quantum key distribution system. It was generating keys. And what we were trying to achieve here is really showing that we could take smart grid communications and then we could implement an information theoretic authentication of these smart grid communications. And we do that using the Carter-Wegman, and these communications are basically broadcast communications. They're designed to work with a publish-subscribe method. So basically, you've got your different smart grid elements publishing, and the smart grid elements that care about a particular part of that message will subscribe to it. And that way, the smart grid communications go back and forth between the users that care, and then what they can do is then make distributed decisions based upon what their neighbors are doing. So this is important if you've got photovoltaic generation as well as distributed energy storage resources. So the trend is that these things are being pushed out of the control center and to local machine learning type decisions to manage the state of the network. And so the lab had a whole framework to do these communications, these smart grid communications that went along with some of the hardware that's been developed at ORNL. And so what we did in this project was to add this, this message authentication to the system. And so now we've demonstrated that you can actually do this and key that based upon these quantum keys that have been distributed. So it's a really strong type of authentication. And so you don't have to worry about potential adversaries trying to ruin your, or be an imposter in your smart grid communications. All right, quantum secret sharing. Quantum secret sharing is another protocol where we seek to go from one party to multiple parties. And so this is a continuous variable quantum secret sharing scheme, which Bing Chi has developed a bunch of theory for, and we're in the process of building it. And the idea here is that we take an amplitude and phase encoding, we apply that to a quantum level signal, and then we send it out to the network to these multiple users. And then at each user, what they do is they impart information to that quantum signal. And then at the end of the day, everyone's imparted something, and then the center node here makes a measurement. And with that measurement, then the parties need to cooperate. And when they do cooperate, then they can share a quantum secret. And it's also extensible such that if one party basically says, oh, this is what I did, then the other two can create a key. And Bing Chi showed theoretically that using this kind of quantum secret sharing version of QKD, you can actually do better than simple QKD multiplexing. So one thing that I'd like to point out that's really novel about this idea, and I give credit to Bing Chi because he's the one who came up with this, is that typically when you talk about quantum secret sharing, what you have to do is you have to directly modulate the quantum signal. And if you directly modulate the quantum signal, what that does is basically put your modulator out there on the open channel, and then it makes it vulnerable to what's a well-known attack called the Trojan horse attack. So someone could shine their own laser in there and know exactly how you modulated it, and so it's got a pretty big security vulnerability. But what's clever about this approach is that instead of putting the modulator in the channel, the modulator is up here in the box. safely in the box, and instead we just send the quantum level light in. It's mixed on this beam splitter, and then a portion of it is retained and measured by this user. So this actually looks a lot like a QKD type system. And so then, you know, it doesn't matter if anybody shines light through this. You know, the modulator is up here, so it's got potentially much greater security than previous approaches. And actually, I think I've given a talk at Purdue a while back where I talked about one of the polarization encoded quantum secret sharing experiments that we did. Let's see. So next thing I want to talk about are a protocol called quantum digital signatures. I'm not aware of many or maybe any people working on quantum digital signatures in the US. We just started a project on it pretty recently. And the idea of quantum digital signatures is basically we want to have some kind of user that starts over here on this side, and we want to establish some quantum resources with other users, multiple users, not just a single user like in QKD. And we want to distribute those quantum resources in such a way that we can then later on be able to use the fact that we distributed quantum resources to these different users to then basically digitally sign a classical message and have all of the other users agree that it came from the person who they shared quantum resources with. And so it turns out that digital signatures are used all over the place right now, but the way that they do it is something that is going to have to get changed because they're based upon public keys. So we're exploring these multi-protocols, and I just want to show that this is like a calculation of what we expect to get. We're partnering right now with Qubitekk, and they're making some sort of customized version of their QKD system core components, and we're going to be working very soon with those components to try to implement quantum digital signatures using polarization and entangled photon source. And so what we've got here is a simulation of what we expect to be able to get with some of the numbers that we got for their hardware performance. Okay, so I'm probably going through this faster than I need to, but now I want to get into networking. And this is a touch point where we've had a lot of progress collaborating with Professor Weiner and Purdue and hosting their students while we were still allowed to do it. We haven't been able to do that for a while due to COVID, but you know, we're really looking forward to doing more joint experiments with Purdue. So a few years ago, we started looking into frequency qubits at ORNL. And the reason is that if you can encode your information in the frequency degree of freedom instead of like the polarization degree of freedom, you can transmit that down an optical fiber. And that optical fiber doesn't really do a whole lot, you know, in terms of if you have the fiber blowing around in the air like we saw in the QKD systems, you know, that changed our error rate pretty dramatically, but it wouldn't change the wavelength of your qubit if your qubit was encoded in the wavelength. So there's also quite a few on-chip quantum light sources that could be utilized, and it's useful for connecting qubits in quantum networks. So frequency is effectively used a couple different ways inside connecting qubits. One thing that you might have is, let's say, some local strain on a qubit, and it'll cause some frequency shift in the natural energy transitions. And so if you want to have good quantum interference, you either have to have a frequency beam splitter to remove that, or you have to be able to do some kind of frequency conversion. And so what we do is we take the first approach and we look at using frequency degree of freedom to do linear optical quantum computing type transformations. And this was really pioneered by Joe Lukens and Pavel Logoski. Pavel had been thinking about doing linear optical quantum computing for quite some time. And this frequency encoding idea that they published in 2017, really, we've done a lot of work using these ideas from the get-go. And it works in a very analogous way to linear optical quantum computing. And so basically what we do is we just pick two frequencies, and in most of the experiments that we've done so far, we're really only concerned with sort of discrete frequencies. So we're operating on CW beams. And so if you pick frequency 1, you call it logical 0. Pick frequency 2, then your logical 1. And just like in linear optical quantum computing that's based on chip and uses multiple modes in spatial domain, what we do is we use the frequency domain. And so the idea here is that we can build up these kinds of unitary transformations and interferometers that what we do is we spread out the frequency using electro-optic modulation, phase modulator. And then what we can do is then manipulate the individual phases of these frequencies and then combine them back together again so that it looks just like one of these multispatial mode interferometers. And so Joe and Pavel showed that you can do arbitrary operations in the linear optical domain. And so then since the proposal was out there, we spent a fair bit of time actually realizing these kinds of things. Initially, we started.
Basic question.
Initially, we started on an LDRD, a lab-directed, internally funded research project. And so, in our first experiment, we showed that we could do these kinds of frequency beam splitter types of things. And that's a 1 qubit gate. This figure in particular, we call that a Hadamard gate, sweeping through those. And then we showed that you could do the 2-photon gate. Of course, the 2-photon gate, it's a linear optical gate, so it's post-selected. So, there are proposals out there that says that you could scale up that gate and get it to be something which is arbitrarily close to 1 in terms of its success probability, but you have to throw a lot of resources at it. So photons, things like that. We also showed that we've got a lot of bandwidth here. And with that bandwidth, it means that you could potentially support up to around 30 qubits and do different operations on those 30 qubits simultaneously. And so that sets you up for doing things like quantum simulation. And I know Joe's been doing some quantum simulations using that. At least up until about 2019, we combined all these things, and it was featured in Optics Photonics Optics in 2019. And Joe and Professor Weiner have been continuing to collaborate and work on this and take it to the next level. Okay, so Joe has been working in collaboration with Professor Weiner on trying to take this stuff that's sort of meter-sized optical tabletop telecom stuff and move it to on-chip. He's been doing this funded under a Department of Energy Early Career Award, which are very prestigious, and only Joe and postdocs can work on that project directly. And so the idea is that when we're doing this experiment, we were very limited to the signal-to-noise ratio with all of the loss in the classical optical telecom components. And so Joe's been looking into how we shrink this onto chip, and it dovetails quite nicely with all the stuff that we're doing at QKD and trying to put it on chip. We have a couple of optical probe stations that we've got. Most recently, we've got a really nice Maple Leaf Photonics optical probe station, and we're hoping that we can combine these on-chip kinds of things with our quantum local area network and do some really exciting experiments. Okay, so we're starting with a practical entanglement distribution in our quantum local area network. And so the basic idea is we start with a source that's really broadband, and that'll be frequency and polarization entangled. And so frequency entanglement comes naturally from energy conservation in the down conversion process, where a pump photon splits into daughter photons. And then the idea is that we can carve that bandwidth out using those energy correlations to define entangled channels that look like this as an example. And so we would have a pump, and then you would basically the harmonic of the pump defines this line here in the middle, and then the energy entanglement means you would get something that would be red or blue detuned, and those would be entangled on either side of the harmonic of the pump. So as an example, we could connect Alice and Carol, or we could connect Alice and Bob, or we could connect Carol and Bob. And then that way we could take the spectrum and use it as a way of remotely configuring the different links. So as an example, there's this paper which was just recently published in Optica, which is a collaboration between Joe and Professor Weiner. And this is the spread spectrum technology, and basically the idea is that you would use a wavelength selective switch to be able to dynamically carve up the bandwidth and assign it to where you wanted to have the resources. So what we've done at the Oak Ridge is to kind of do this experiment that was a tabletop experiment, and to kind of put it on steroids and try to get it to work between multiple laboratories. And as I mentioned earlier, just like in the QKD case, once you start putting things in different buildings and they're not all sitting on the same tabletop, the complexity of the experiment goes up quite a bit. And so in this particular experiment, what we did was we started with this type 2 periodically pulled lithium niobate source, and then that generated lots of entangled photon pairs across many optical channels. And then we went into WSS, which we used then to configure what part of the spectrum went to what laboratory. So we had, in this experiment, we had 2 sets of superconducting single photon nanowire detectors, one in this laboratory, and then one in this laboratory, and then in this laboratory we had some indium gallium arsenide single photon detectors, which aren't nearly as good. They don't have a very good duty cycle. They're pretty noisy, and they don't have a very good detection efficiency. But nonetheless, we were able to get this to work, and we were able to get this system to work and distribute a clock using an RF signal, basically an optical RF over optical signal. And that was actually pretty important, also one of the hardest things to do in this experiment, since when you have a not great clock, it forces you to have large windows of time to look for the first entangled photon and the second entangled photon. And since that window is large, what it opens you up for is seeing one legitimate photon and then some noise photon from someplace, even if it's from another entangled photon pair. And we call those accidentals counts. And so that actually sort of hurts your entanglement quality quite a lot. Although when we look at the next slide, so here's the next slide where we kind of show this conceptual layering of what happens in a network on the left-hand side. Immediately below that, we show what the individual measured fidelities are of the different links. And then what we did was we calculated the entanglement quality in terms of this negativity measure. And then we looked at the rates that we had in the throughput, and we're trying to figure out if it makes sense to analyze these links in a sort of entanglement quality times an entanglement throughput metric. And up here, it just shows that with this wavelength selective switch, you can set up your network such that they're densely connected. Okay, so now that you have entanglement, what do you do with it? And so what we did in this particular case is we did an instance of remote state preparation, which is a quantum communications protocol that's kind of similar to teleportation, but it's a little bit easier. And the idea here is that in teleportation, what you do is you take a quantum bit that's unknown, you share entanglement with someone, and I take that unknown bit and I do a measurement, a joint measurement between that unknown qubit and my half of the entangled pair. And then I send that measurement off to the other person to perform a unitary operation. But when you do that, you don't learn anything about that incoming qubit. Remote state preparation does something a little different, where I share entanglement with somebody, and I want to basically have them hold a particular quantum state. And so what I do with my half of my entangled pair is I take and project it into a particular measurement basis, where the result of that measurement basis is the thing that I want to remotely prepare. And then if it works, it's non-deterministic, then I would send a classical signal off and say, keep that one. Okay, so this is, so we did this for, I believe it's the very first networked demo of remote state preparation. And so here on the right-hand side, we show example remotely prepared states between the different links. And we get pretty good fidelity given the quality of the entanglement that we get due to those accidentals limitations that I mentioned earlier due to the wide coincidence counting windows. Okay, so hybrid all-optical quantum repeaters. So one of the things that we want to do is figure out how we can build quantum repeaters in a way that's tolerant to the noise sources that we see on optical networks. And so early on, the concept for building quantum repeaters falls into this category that's shown here, this generation 1 quantum repeater, where it looks just like this trusted node QKD, in that we're breaking up the link into smaller links, and then we perform operations. And the problem with this approach, or I should say limitation of this approach, because it could still work on smaller scales, is it requires you to do two-way classical communications. And those two-way classical communications means that you have really strict requirements for quantum memories. And ultimately, it doesn't really scale terribly well if you're looking at like a continental scale distance. And so the theorists have come up with these third generation quantum repeaters, which are really quantum error correcting codes of photons, which then you go to a quantum repeater node. It's like a special type quantum computer. You do quantum error correction and encode your quantum information on freshly created photons, and they set it off to the next quantum repeater node. So I just like to note that when you go to this generation 3 type approach, you can't have more than 50% loss over the link, because you basically lose the ability to do the quantum error correction. In practice, they probably tolerate a lot less, at least with the codes that we know about today. But the advantage is you can get arbitrarily close to like more of a deterministic type transmission, and you can do it fault tolerantly. And so you can make up for loss errors as long as the overall loss isn't too much, and you can make up for operations errors. And so this approach is really what we know about today, which could in principle give us something that looks more like a classical network in terms of its performance. And so what we're trying to do is develop some theory and some experiment to inform the theory, so we can understand how putting this on an all-optical network breaks it and allows us to make more resilient codes. Okay, so I managed to get through all of that on time despite my bit of a technical difficulty there. So I'm open for questions, and I want to say that we've been really fortunate to collaborate with Purdue, and want to keep on doing that. And our laboratory is growing. We're trying to build a quantum information science section at ORNL. And so that means we're going to go from about 20 people working full time in this area to maybe 35 or 40 or 50. It's not exactly clear how how far this is going to scale, but we expect additional investments in QIS, and it's a big priority at Oak Ridge. We're going to be moving to 9,000 square feet of lab space that's state of the art in a new building that's being built, the translational research capability. And so it's a really exciting time to be doing QIS at Oak Ridge.
Thank you. Thank you very much, Nick. We have time, quite a bit of time for questions.
Yes, hi, this is Andy. Nick, thanks for a great talk. You covered a lot of ground. And I'm hoping your speakers are on now so you can hear. I was wondering if you could elaborate just a little bit on, you mentioned, well, a number of nice things from being Chi, but in particular, it mentioned that some of the CV techniques were more tolerant, I believe it was, to the Raman noise than the discrete photon techniques. And you had one graph up there that I couldn't fully grasp, but generally I just wondered if you could elaborate a little bit on how large is the difference? What is, how large is the advantage that one can get with the CV relative, to the discrete photon versions?
That's a great question. I haven't included it here, but at least in the context of QKD, so there's a lot of caveats that are built in. So the security of discrete variable QKD is much more rigorously understood compared to the continuous variable QKD. All right, so there's not exactly an apples to apples comparison there, but what people have done with CV-QKD is they've shown that they can do it over links which have been fully loaded up with multiple data transmission channels. And so basically, if I have a discrete variable single photon detector, they tend to see really, really broad amounts of spectrum. And in the discrete variable case, if you have one noise photon come in and you have one quantum photon come in, now your signal to noise ratio is 1 and you're in trouble, right? So those types of single photon noises that you get from Raman scattering very strongly limit your ability to see the quantum channels. In the context of that CV case, we're typically using really narrow lasers. So like, on the order of like, 100 kilohertz or less. And so that defines the amount of bandwidth that can come in and foil your noise signal. So now this is a little bit inside baseball, but it's related to the security proofs and how we make assumptions on the different protocols. So for CV-QKD, we use something called the trusted noise model. So we have to very accurately calibrate the noise of our detector and trust that detector noise in order to be able to generate quantum keys, whereas we don't necessarily have to make that same assumption in a discrete variable case.
Okay, so there's a lot hidden there. Great, thank you. That was helpful.
So may I ask a question? This is Vlad Shalai. Well, first of all, thank you. Really nice presentation, very educating and great progress. My question is related to quantum repeaters. So you largely discussed all optics-based quantum repeaters. So to send a signal really for long distances, I guess the key thing for quantum repeaters is actually the coherence time, for how long you could actually keep it. And in that regard, moving from optical system, like for example, spin system or other with a relatively long coherence time could be advantageous. So what are your thoughts on this? Do we really want to have quantum repeaters all optics based? Or maybe it's better to use other degrees of freedom with longer coherence time?
Well, I'd say that that's an open question right now. So we had a workshop before COVID shut everything down. It was called the Quantum Internet Blueprint Workshop, right? And so, we had the sort of well-intentioned goal of going in there and sitting down and saying, well, how can we build a national scale quantum internet? And I led one of the discussion sections, and to be a little bit provocative, I suggested that we don't know how to do that yet. And everyone just kind of looked at each other and said, yep, we agree with you. So I'd say that right now it's not exactly clear how we're going to do it. I mean, there's all optical approaches. There's approaches where we might potentially be doing links and transduction to quantum dots and things like that. And I think as we push on the technology, really what it boils down to is not just the coherence time itself, but how well we're able to correct for errors that just naturally pop up, right? And so we don't understand how to do that yet. It is definitely related to solving quantum error correction problems in quantum computing, and that's something that people have been working on, actively for a long time. There was a multi-year program that came out of IARPA to try to figure out how to build quantum error correction and have a logical qubit, which could be thought of as a memory, a logical qubit, where the errors in that logical qubit are less than that of the individual physical qubits that make it up. So, that's something that people are definitely working on right now.
Yeah, can I ask a question? I have a rather naive question to ask because I have not worked too long in this area. And also I had the lecture this morning. I missed most of the lectures. It seems that you have all the necessary components to make a quantum FFT or maybe quantum Fourier transform. That seems to be a low-hanging fruit and is very important for electrical engineers. How far away, or maybe you have already made them, your ability to do quantum Fourier transform?
Yeah, I think that's something that people can do. It just depends on how big you want to do it. Obviously right now with the state of the art, we don't have a ton of qubits. Like if you look at the different approaches, and one of the challenges when we add a new qubit is crosstalk. And so if you look at some of the people who are out there pushing on quantum computing, sometimes when they add a new qubit, they don't actually fully connect it because it makes the system work better in terms of like having crosstalk errors and things like that. So, even small things are possible, but when you try to go to the next biggest step, it becomes more difficult. So it just depends on how big of a transform you want to do.
Okay, thank you.
Maybe I can also make a very general question. Since you're author of many of these strategic reports, so of course, in the area of quantum computing, people talk about, of course, as you mentioned, we still have small number qubits. We're dealing with a NISQ, noisy, small, this intermediate scale device. Maybe we can't solve some large problem like factoring numbers, but maybe there's some low-hanging fruit. It will start to make a first impact. Some people say it could be quantum chemistry. Now back to the quantum communication. Of course, the hardware still have limitations. People talk about bandwidth is low. You talk about the distance of you can reliably send store for that. Even all these limitations. What are some low-hanging fruit that even not so perhaps perfect quantum communication can already make are already making an important, say, practical difference?
So first of all, I guess there are things where we could apply quantum techniques, and the goal is to do better than you can do using any classical method, right? So some people call this quantum advantage. And so we expect to have some things in the computational space, which hopefully be accessible to us, hopefully before too long, and simulating, quantum spin liquids, and things like that. Hopefully we'll have a real computational advantage with some things that we can do soon. We already see that squeezing can drive down the noise floor and improve sensitivity in doing experimental measurements. LIGO is an example of that. We've been doing experiments, particularly Raphael Puzer's been doing a lot of experiments showing that that's a really practical way to get an advantage out of using quantum resources. And then there's things that you just can't do any other way, or not practical any other way, like the quantum key distribution application. So I think those are kinds of the kinds of low-hanging fruits that are out there, and basically getting these systems to routinely give you a quantum advantage, and then applying those to especially like domain science problems, and trying to develop new algorithms so that you get an advantage with fewer resources.
Okay, thank you. I was specifically referring to the analog of quantum advantage in the quantum communication, but I guess you identified as the QKD as one of the important low-hanging fruit in communication.
Yeah, and QKD is one of those things that, even though it's one of the most mature quantum applications, it's not nearly as mature as classical cryptography. So, even though you can go out and do demos, there's still a lot of work that has to be done before people are going to be comfortable using it.
Okay, thank you.
Yeah, I have one more question that I'd like to ask you. Because I'm a classicist in electromagnetics, and one of the very challenging area that we do is actually array antenna design. Because if you don't design array antennas properly, you get blind spots or squint spots. And I noticed that the Chinese scientists put together a very sophisticated phase lock loop to get the quantum advantage that they need to reduce the noise in the system. For your kind of work, do you need phase lock loops, or can phase lock loops be used to reduce quantum noise in your problem?
Yeah, it depends on exactly what you're trying to do, but my expectation is that in some cases, phase lock loops could be actually very useful. So if we're looking at these kinds of continuous variable systems, if we were to sit down and design a continuous variable quantum repeater, my guess is you would have to have phase lock loops.
Okay, but it's not routinely used in quantum communication. I guess it's difficult to use since you're talking about very long distance communications.
Yeah, I mean, as far as I know, it's not really routinely used by the community, but certainly as we push on performance, there's probably going to be a point where those are going to be useful. I mean, they are useful for coherent communication systems.
Okay, thank you.
Any other questions? Okay, well, if not, thank you so much again, Nick, for your very informative presentation. I guess, and thank you again for later. We'll do another meeting this afternoon. So see you.
Well, thanks for having me. It's nice to be able to start this conversation that I think we're continuing to have with people and trying to figure out how to grow and to collaborate and to push this technology so it actually does stuff to benefit people.
Yeah, look forward to expanding the collaboration between us. Thank you. We can talk to you later.
All right, thanks. Bye.